Well, welcome everybody to Pure Virtual C++ 2024. I am your host, Cy Brand, and today we have 2.5 hours of C++ content for you all. We have 5 talks. First up is going to be Keith Stockdale talking about automated testing of shader code. Ben Dean from Intel will talk about message handling with Boolean implication. Then I will talk about how I embedded a programming language in debug information on Linux. Sinan Makinja will talk about enhancing C++ development with Copilot Chat. And finally, Zachary Henkel will give us a progress report on adopting header units in Microsoft Word. Please do use the chat on the Microsoft Reactor YouTube. We will be keeping an eye on them, answering questions. Please do keep in mind that we have a Microsoft Reactor Code of Conduct, which you can see on the screen right now, and we will drop a link in the chat as well. Just make sure that you keep your comments respectful and friendly, please and thank you. We do have a bunch of on-demand content already available, which is all you can find at this link here. That has a whole host of C++ content on a variety of C++ topics, so please do check all those out. And the last thing before we get started is we do have a survey. It would be great if you can fill this out to let us know what went well in the event, what we could improve for next year, and just so we can keep in mind what you all think. So without further ado, I will introduce the first speaker, Keith Stockdale, who's going to be telling us about automated testing of shader code. Welcome, Keith.
Hello. Nice to be here.
Hello. All right, take it away.
All right, then. Okay, so this is automated testing of shader code at Rare. My name is Keith Stockdale, and I'm a senior software engineer at Rare. And I've given a talk on this topic just at this year's GDC, but this is going to have a bit more of a C++ spin on it. So a little bit about me first. This is me, in case my video quality is a bit poor. And if you're wondering, the accent's from Northern Ireland. That's where I'm originally from. And I've been working at Rare for the last 6.5 years on the engine and rendering teams. Basically, my whole job is just writing things on the GPU that probably shouldn't be run on the GPU. And at my time at Rare, I have worked on Sea of Thieves. Sea of Thieves is a game that we launched initially in 2018. It is our first Unreal Engine game, and it is based on a very heavily modified Unreal Engine 4.10, so quite old. And I said we initially launched in 2018 because we have been consistently putting out updates throughout the years. Just last week, we released a major update, and today, in fact, we released for the first time on PS5, which we're all very happy about. So still lots going on with Sea of Thieves, still very much in development. And alongside the development of Sea of Thieves, we also have Everwild. And Everwild is our up-and-coming game at Rare. And it's a little bit different with Sea of Thieves in that we are trying to stay up to date with the latest and greatest Unreal Engine. So currently, we're on Unreal Engine 5.2, and we're in the process of upgrading to 5.3. Okay, with all that out of the way, the problem. And the problem that we have at Rare is that we are writing more GPU code. And this GPU code is not your typical GPU code that outputs pixels. It's more general purpose simulation code. So just in Sea of Thieves, we have 2 very prominent GPU simulations. So the first is our FFT water simulation. So you can't really have a game called Sea of Thieves without having a very good looking sea. So that is all being simulated on the GPU. And then we also have our GPU particle simulation. So anything to do with fire or sparks, fireworks, smoke, bubbles, water spray, all of that type of stuff, that's all being simulated on the GPU. And with all of this general purpose code being executed on the GPU, we like to test it. And the reason for that is because we as a studio love automated testing. And we love it so much that we have given a number of talks on it, this one included. One particular talk was automated testing of gameplay features in Sea of Thieves by Rob Masella way back in 2019 at GDC. These are some links if you want to go to it. If a QR code's easier, there's a QR code. Otherwise, some words. But this is the main slides that I felt was the most prominent thing on his presentation, where he's talking about all the benefits that we have reaped from automated testing. So we've got things like reduced time to verify builds, so we get our content out to players much quicker. Lower bug count with comparison to previous rare titles, and observably reduced crunch as well. So these are all the reasons why we like to do it. But Rob here was talking about testing of gameplay features, but I'm here to talk about testing of shader code. And if you don't know how to get started with testing shader code, this is a fantastic article by Bart Ronsky. It's called How Not to Test Graphics Algorithms. And in it, he lays out two main ways of testing graphics algorithms. The first is screenshot testing, which is what we've been doing at Rare since before I started back in 2015. And then the second approach is what I'm going to be talking about today, which is shader unit testing. So our unit testing framework for shaders, we just called it Rare Shader Test. And it is a testing framework for HLSL codes. And if you don't know what HLSL is, it stands for High Level Shading Language. And it is the shading language that all DirectX applications use as their shading language. So if it's a DirectX app on the PC, or if it's an Xbox game, chances are the shader code will be written in HLSL. Our unit tests are written in HLSL 2015, so quite an old version. And the main reason for that is because our testing framework is being used for both Sea of Thieves and Everwild. So 2015 has a common feature set there, so we stick to that. And it runs on top of an Unreal testing framework. So this is not a standalone testing framework by all means. It is just adding on top of what Unreal already gives us, so that we can use all the nice tooling that Unreal provides, as well as letting us test our shader code. An example of the testing framework that we are building upon is CQ test, which stands for Code Quality Test. And because I know in the audience there are probably at most one or two people who actually know what this is, it's an Unreal Engine testing framework, like I said, and it's available from Unreal Engine 5.3 and on, so it's fairly recent. It's quite comparable to Microsoft's unit testing framework, and if you haven't seen it before, this is what a testing suite might look like with CQ test. So you have your test class macro at the top, and that defines the actual name of the test suite. And then you have a number of test methods within it, which are your actual tests that run. Within your test methods, you'll have various assertions, basically just making sure all of your code works as you expect it to. And then in addition to test methods, you also have setup methods called before each. So these methods will be called before each test method, as well as after each. So that'll be called after each test method to do some cleanup. Now, before I go any further, I want to just make it clear what our coding environment is. Unreal Engine 5.2 currently, so we are upgrading soon, but very much still on 5.2. And that means we're in C++ 17 land. So we unfortunately don't get the nice C++ 20 just yet. That will be coming with 5.3. So another reason why I'm very excited about 5.3. And we are using HLSL 2015, as I said. Now, throughout the course of this talk, I'll be showing C++ code as well as HLSL code. So if you see the C++ symbol at the top right, it'll be C++ code on the screen. And if you see the HLSL doggo, you will be seeing HLSL code. Okay, then, on with actually showing how to write a shader unit test in our testing framework. So HLSL doggo at the top right, this is HLSL. So it starts off with some includes. So at the minute, it kind of looks like C++ with the includes. The first include is the header that all Unreal shaders must include. So there's nothing interesting there. Then we have the actual testing framework. I'll be talking a little bit more about that header later on. And then we have our system under test header, which is, in this case, the water particle framework. And then we have the first clue that this is not, in fact, C++. This is a shader. So this is an attribute that you tag on to the entry function of a compute shader to tell it how many threads to run per thread group. So this is a very simple shader. It is running a single thread. So not very good use of your GPU, but we don't really need it to be very fast. We just need it to be correct. And then we have the entry function. And we name the entry function the same name as the test. This just makes it easier to connect up the HLSL side to the C++ side. And at Rare, we like to use the given, when, then naming scheme for writing tests. So in this case, we have got giving moving water exists. So we construct some water with a known velocity. When the particle is spawned on the surface, so in this case, we're passing in water into the spawn function, and it returns us a water particle, then the velocity is inherited. So we assert that the spawn particle's velocity is in fact the velocity that we expect it to be. And that's basically it. So you've got your standard given, when, then that you might see in any other testing framework with any other language. Now, this is a shader, so we need some C++ code to dispatch the code itself. And we try to make sure this is as minimal boilerplate as possible. So we start off with the header of the testing suite, which looks like CQTest test class macro, except it has an extra argument. And that argument is the path to the actual shader test themselves. And then we have any number of test methods. So again, it's just giving the method and giving the name of it. So you can search that name and you'll find the C++ code as well as the HLSL code in your code base. Now, the shader I just showed is extremely simple. It has no external parameters to bind or anything like that there. It'll just run with nothing to provide in the C++ side. So all we need to do is call run compute shader test with the dispatch configuration. So if you're familiar with DirectX at all, this will be equivalent to calling dispatch 111, right? So it's dispatching a single thread group on your GPU. So it's a single thread group, and that single thread group will be running a single thread. So not very fast, not making use of your GPU in any way, shape, or form, but that's fine because the main thing we're concerned about here is testing our code on the actual hardware that it would be running on during your game. Now, at this point, I want to talk about the goals of the framework. And initially, I was going to talk about all of them, but just for the sake of time, I'm only going to talk about two. The first is we want our test to be fully automatable. So I mentioned that we have screenshot testing for Sea of Thieves, and we've had that for ages. But the problem with it is it's not fully automatable. We do require our test team to verify screenshots from time to time to make sure everything is still right. However, that's not ideal. We'd rather them just get a green tick for happiness and red tick for sadness. So to demonstrate that this is actually something we can do now, we have this feature in Sea of Thieves, which is our calm water system. And what it'll do is, as you get closer to an island, it will smooth out the FFT water simulation. So in the distance there, you can see it's all very choppy. But then as you get closer, it smooths out quite considerably. And we have a full test suite just for this feature. And the nice thing about building on top of our testing framework in Unreal is that we get all the nice Unreal test running capabilities as well and reporting. So we can just open this up in our session front end like anything else, hit run on all of them. So there's 29 tests and they run lightning quick. So there are 29 tests here and they're running in about 0.3 seconds. So about 10 milliseconds a test. And that is lightning quick, especially if you consider how slow screenshot tests can take. So yep, fully automatable. We were happy with this. And then right to goal number 5, error-driven development. And what I mean by this is if you get an error as a developer while writing the test in the framework, that error should tell you how to proceed. So it tells you what you did wrong and how to fix it. Now to give a demonstration of that, we have a slightly more complex shader test here. So instead of just passing in the dispatch configuration, we are passing in a setup function. And within that setup function, you can set some parameters on the actual shader itself. I'll go into more detail on this later on in the talk. But suffice to say, the developer writes this, it looks right. But you'll get a compilation error, and it's not a massive big litany of template errors. It's actually just a single line, which says expected a single parameter of f shader test context reference. So it is very, very common. It's very easy to just miss out an ampersand, right? How often have we seen like performance regressions because we accidentally forgot the ampersand in a sorting functor, right? So we do as much static reflection at API boundaries of functions that are templated, as much static reflection as the language currently allows us. We're not quite at the land of static reflection proper yet, but I'm very hopeful for C++26 to get us there. So yeah, as much as we can, and then we static assert and give nice error messages. Now you'll notice here that I'm not able to actually format the message. I'm not able to say what they did wrong. I can just tell them what they need to change something to, or to make sure that the parameter is a reference rather than just passing by value. And that's because we don't really have user-generated static assert messages, right? It's currently not possible. These have to be string literals. You can't do std format or anything like that with them. At least it's not possible for us. Depending on what your development environment is, it might be possible for you right now, because it got accepted into C++26. Very happy about that. We'll get there soon, maybe, possibly. And it's implemented in Clang 17 at the minute, and I think it'll be making its way to GCC 14. Still no word on MSVC yet, which is the compiler that we use. But some people might be able to use it, and I'm very excited for them. These are the links to the discussion on it, basically seeing the progression of it, and also a link to the paper. It's all of the points that Corentin brought up in his paper are basically all the things that I want. So yeah, rationale is solid there. Definitely worth a read. Now, binding extra shader resources. In the previous example, I talked about binding extra parameters, and we do a lot of static reflection whenever we're binding extra shader resources. And to give more of an example of what that actually means, is if we have this test shader here called test with extra parameters, very imaginative name, and we have these parameters themselves. So we've got a byte address buffer and we've got an integer and float. So if you've got a non-static global variable in HLSL code, that is a shader binding. So that is an object that you can bind to on the C++ side to pass in information to be used within your shader. And here we're just asserting on them, essentially. So to be able to do this, you need to do a bit of extra work on the C++ side. And the nice thing about Unreal is it provides some nice macros for us to do that. So if you've written any rendering code in Unreal Engine, you'll have seen this macro here. So begin shader parameter struct, we give it a name, and then we just pass in all of the parameters that we are going to be using. So in this case, it's our byte address buffer, our uint, and our float, and we ended off with an end shader parameter struct. However, this is wrong, and we'll get a nice compilation error here out of this. It will first say the test shader that this test uses has a parameter struct which does not contain the base shader parameters. It might not shock you to believe that the test framework itself requires extra parameters to be bound, because whenever we are running asserts, what that's doing is logging some information to a buffer behind the scenes, and then we read back that on the GPU, on the CPU. So it needs its own parameters, and whenever we just use this begin shader parameter struct for ours, we're not including the ones that are required for the test. So how do we get around that? Well, thankfully, the error message continues. It says to fix this, please use begin CQ test shader parameter struct. So it's telling you that the thing you need to change. So change begin shader parameter struct to begin CQ test shader parameter struct, and that will fix things for you. And then it continues and says the line below this one is the test that uses this invalid shader. So we're telling the developer that it is the test that is signified in the next line of the error message that is the problem. So we're telling people where the issue is, what they did wrong, and how to fix it. So this is what I strive for in this framework, just to make it as easy as possible for people to write tests without having to go diving into the documentation off somewhere else. So all of this is predicated, all the static reflection is predicated on being able to detect invalid expressions. And in C++20, this is quite trivial. You just use concepts. So you have a concept here. I've just called it C has shader test parameter struct, and we have a requires clause here. And within our requires clause, we will define some constraints. And essentially, if you pass in a T to this concept and these constraints hold, so they are valid constraints with this type T, then the concept will evaluate to true and everybody is happy. So you could just static assert on this because the evaluation of a concept is a Boolean expression, and if everything is fine, turns true, everything's good. If it returns false, then the whole concept framework gives compiler writers the opportunity to provide good, helpful compilation errors. However, I did say that we don't have the luxury of C++20 just yet. So what people typically do in this situation is lean back on void T. But there's another way that I want to talk about today, which is what I would call emulating C++ concepts. So it's trying its best to make it look like it if you squint hard enough. So we start off with a non-templated struct called C shader test parameter struct. So it's the same name. And then we have a templated requires function declaration. And in this, we're just passing in a type T, just like with our concept. So if you start squinting, it's starting to look almost there. And the return type of this requires clause is a decal type. And the decal type will evaluate to this expression. So it's our constraints. So yeah, if you squint hard enough, you will see that this is somewhat concept-y like. One of the differences here is that we're using the comma operator rather than having semicolons. And the reason we're using the comma operator here is because we're sort of abusing it a bit. The result of the comma operator is the left operand and the right operand, and then it returns the right operand. But if any one of these expressions is ill-formed, then the whole expression is ill-formed. Therefore, the type that's returned by the decal type expression is ill-formed. So the whole requires function is thrown out. It is ill-formed. It does not exist. Sphene kicks in. And then to make use of this in a static assert, you don't obviously get the automatic conversion to the operator bool like you do with concepts. We instead pass this concept in to T models, which is the driver of this feature. And you can see here, this is our lovely error message whenever you get this. Now I'm going to go through the actual implementation of this because I haven't actually seen it anywhere else. Although then again, I haven't really dived into too many template meta programming libraries, but I thought it was pretty neat. So I'll talk about it. So it starts off like any other templated meta function. It's a templated struct called tModels, and it has a function here which will return a reference to a character array of 2 elements, so 2 characters, if the concepts requires function is well formed with the arguments passed into it. So if everything's well formed, everything passes, then this function will exist. If it doesn't resolve, if the requires clause is ill-formed, then this function will be created instead. And the difference here is that it returns a reference to an array of 1 character. So there's a size difference here, and you can probably see where I'm going with this. The output of this expression is then basically asserting that the result of resolve is of size 2. If it's of size 2, everything's well formed, everything's good. And it goes even further. You can do a little bit of, I'm not going to call it subsumption because subsumption is very complicated and it's got well-defined rules. So I'll say inheriting, so you can inherit concepts using the refines clause. And that's about it, really. And I just want to talk a little bit about a future goal I have with this framework before I end. And that is HLSL 2021. I mentioned at the start that we are stuck on 2015 for now, but I really want us to get to 2021. And the main reason for that is we get templates. And I love me some templates, but the main reason why templates is a great thing is because it allows us to program to an interface rather than to types. And if you've written any amount of automated testing in the past, you'll know that dependency injection is your best friend, right? And with templates, we get static polymorphism, which is nice way of getting dependency injection somewhat into the language. And it allows us to write much more expressive code. And it is easier to write and share HLSL libraries. But the problem is, it's a breaking change to go from 2018 to 2021. So I'm going to fight that battle, but I'm not that sure how far I'll get with that one. But if you do want to see what a testing framework in HSL 2021 looks like, look no further than mine. So I have an open an open source project on GitHub. Anyone can go and see it. And it's running shader tests on GitHub Actions and all of that fun stuff. So it's got a full CI and everything going, running shader code tests. And the nice thing about it is, well, the main goal of it is just to experiment and see what a testing framework can look like in this language. And I'm heavily basing everything off Catch 2. And by that I mean I'm just taking every feature that I can from Catch 2. I really like the framework, and I want to see how far you can get to it in shaders. But yeah, that's basically it. So I just want to leave you with a nice thing I like to say. Shader code is code. Please test it. And that's about it. So if there is any questions, or if there's even time for questions, I can answer them.
Hey, yeah, thanks very much. It was really interesting. We have a few questions and a few minutes for them. The first question is from Vishal Oza, who asks, can this code be used with GSL?
GLSL.
Yes, GLSL. I assume is what they mean.
I see no reason not to. It's just I haven't used GLSL since university days. I'm sorry. I've been at Rare too long.
Another question from Leslie Lai is how do assertions work on the GPU?
So assertions. So I go a lot more in depth into this in my GDC talk, but effectively at the bottom of an assertion, if an assertion fails, it'll write some data to a buffer with some sort of information on it. So the type of data that failed, the data itself, and what kind of assert that failed. And then we read that back on the CPU and then assert on that data using the underlying testing framework that we're building upon. So yeah, it's all a big lie around a readback buffer, essentially.
Cool. Question from BS Doobie: is screenshot testing still a thing? Why not just grab the state of the rendering pipeline just before all the pixels are colored?
That would be huge. Screenshot testing is still very much a thing. It's something that we rely on quite a lot at Rare, especially on Sea of Thieves. It has been extremely beneficial throughout the development of Sea of Thieves for us. Like, it has shown up so much stuff for us and has caught a lot of things before getting to release. So maybe I can speak for us at least. It is very much a thing for us. I don't know about other studios.
Cool. And one from Das Candy. Can this be extended to GLSL, which you also already answered, but also Spear V, OpenGL, or Vulkan?
Yeah, that is something I sort of want to try, because yeah, you can compile HLSL down to Spear V and then run it in Vulkan, and that'd be something really cool. I have a pipe dream of getting that to run on my Raspberry Pi 5. Like, I think that'd be really cool to get that to run just like on on my own Raspberry Pi server. Something I want to try.
That sounds cool. And a question from Peter Nimmo for me is, speaking of Catch 2, in the future, will there be more support for testing frameworks in Visual Studio? Yes, we're still very much working on other testing frameworks for the Test Explorer in Visual Studio, and cross-platform testing, remote unit testing, all that kind of stuff. So yeah, keep your eyes out for more in that space. And then I think we've got time for one last question from Michael Volling, who asks, have you all had issues with developers forgetting to register tests? That's my biggest fear with manually registered tests.
These are not manually registered. As soon as you write that macro test class, that's it in. It's a static registration on. Yeah, so that can't happen. You can opt out. So like, you can say this test should not run on server, for example, if it's a client only thing. But it's auto registered. Yeah.
Great. All right. Well, thank you so much for joining us, Keith, and hopefully see you around.
See ya. Thanks very much. Bye-bye.
Great. Okay. So next up, Ben Dean is going to be telling us about message handling with Boolean implication. And I'll hand that over right now.
Hello, welcome to Message Handling with Boolean Implication. My name is Ben Dean. I'm a principal engineer at Intel, where I work on power management inside the CPU package. I work on the team with Michael Case and Luke Valenti, and we're using C++20 to bring abstractions to that highly constrained embedded environment. This talk reflects a small part of that. Before we start, some quick disclaimers. All the code you're going to see is simplified for slides, but it is real code that exists in Intel's compile time initialization and build library, and you can find it on GitHub. This talk is shortened for pure virtual C++, so let's get into it. This talk is about a message handling library. Now, message handling is a common problem in many code bases. Maybe many of you have code bases that do message handling. You get some data off the wire or from some other external source, and you need to decide what it is and how to deal with it. And that usually means looking at some of the fields inside the message and dispatching accordingly. So we'll talk about how this library does that in a compositional way that minimizes the work needed at runtime. First, we'll see how fields and messages are defined in this library. Then the idea of a matcher that identifies messages so we can dispatch them. And then, for the bulk of the talk, we'll dive into how matches are composed together and how they're simplified. To begin with, I need to give you a bit of background to make sense of what's to come. So let's look at some nouns of the library, messages and fields that make them up. We can define a field by giving it a name and a type. That type is its API type, if you will, the type the field presents to the outside world. For our purposes, it's almost always a fundamental type and trivially copyable. And then we need to specify where the field lives in the data layout. Conventionally, we do this with the word index in the message and the span of bits within that word. Notice here that the bit range includes both the least significant bit and the most significant bit. At this layout level, we're dealing with data in bits, and it's common for fields to be just one or a few bits. Here's perhaps a familiar example of a message. This is the IPv4 header as seen on Wikipedia. It has some fields here, version, internet header length, and so on. Let's see how a few of them look in code. This is what definitions for those fields look like in C++. Each has a name and a type, and then a locator for where it lives in the data layout. Version is the first 4 bits, IHL the next 4, etc., etc. A field knows how to read and write a value of its type into the data layout. We call those functions extract and insert, and this is what they look like. The range here is any range, like an array of bytes, for instance. Notice here that a field is just a definition. It's an empty type. There's no value in a field. The value is in the data, and the field knows how to deal with it in a type-safe way. So now, a message definition is just a collection of fields. It's also an empty type. To make an instance of a message, we put together the definition with the data. This is what it looks like in C++. The message is effectively the type list of fields. Owning here is a type alias that provides a right-sized array and get and set methods so we can use them to read and write field values. And there's some UDL machinery here to make the interface a bit nicer. But that's all there is to field and messages. Machinery in the type system that allows us to make these things in a declarative way and work safely on the plain data underneath. Okay, so now we know what fields and messages are. Let's look at how to identify messages that come off the wire using what the library calls matchers. What's a matcher? It's a predicate on a message, a function object that, given a message, returns a Boolean value. Here's what a concept for a matcher T might look like. Now, I'm cheating a bit for the slide. Assume we have a prototypical message here. So when we call the matcher on that message, it gives us back a Boolean value or something convertible to a Boolean. You get the idea. Here's a concrete example. If we want to dispatch based on a certain field being a certain value, here's a matcher that does that. So when we call its function call operator with the message, it's going to extract the right field and test to see whether it's the right value. Okay, it's quite straightforward. We can make that equal to matcher a bit more generic by templating over the relational operation. Instead of just equality now, we can pass in the operation we need. And the standard gives us function objects for less, greater, etc. So we can use those. Now we have matchers that can test equality or whether a field is less than a certain value, etc. And we can use template aliases to make it as easy to use as the concrete equal to version we saw on the last slide. Now, a matcher is a predicate. It's a function that returns a bool. So we can compose matchers just like we compose bools. If we make class templates for and, or, and not that wrap the underlying matchers and implement the function call operator, we'll be able to compose matchers in an expression template. Here's what that looks like in C++. When we AND together two matchers, we wrap them in an AND T. And the function call operator here does the obvious thing. It calls the two wrapped matchers, ANDing together the results. I bet you can guess what OR looks like. It looks just the same as AND, except with OR. And NOT is even simpler because it only wraps one matcher. Notice that AND T, OR T, and NOT T here are still matchers. They all implement the function call operator, taking a message and returning a bool. So now with AND, OR, and NOT operator overloads that work on matchers and return the appropriate wrappers, we have a simple expression template thing going on. Now we can combine matchers with the usual Boolean operations. Let's pause for a second and see what we've defined so far and what it looks like in code. We've got ways to define fields and messages. We can declare a callback. That's the combination of a matcher and a function. When we get some data off the wire, if the matcher matches that data, we're going to call the function. That's what handling a message means. And the handler wraps up the callbacks so we can call a handle function with the raw data. You can see here how we define a matcher in user code. That type field equals 42 is a little DSL that ends up being an equal to matcher that we saw before. And then the function takes a const view of that message. That's another message instance type, like the owning type that we saw before, except this time it's just a view type. But it has all the same type-safe machinery for reading fields. Here's another example of that matcher DSL. The AND and OR operators here are what we saw before, and the relational operators are overloaded to produce the relational matchers we saw before. So this ends up being a convenient way to express matchers. Bear in mind the expression you see here becomes an expression template. It's an empty type that expresses the constraints on fields in a message. All of the literals you see here are compile time values that get put into the type of the matcher. And the resulting matcher itself is a template expression tree. Now, we've made it easy for users to express arbitrary matchers, and we'd like to make sure that doesn't translate into unnecessary work at runtime. All of these matchers are empty objects whose semantics are in their type, so we'd like to take advantage of that at compile time and do the least work at runtime. At this point, I had to think for a while. These are the kind of expressions I thought about. How is the library to know how to simplify things like this? We can look at these expressions as humans and understand, for example, that less than 5 or greater or equal 5 will always be true. Less than 5 and less than 7 requires us only to check that the field is less than 5, because if it's less than 5, then it's also less than 7. And the last thing here is saying that the same thing on each side of the AND. Not less than 5 is the same thing as greater or equal 5. So now we come to the real problem of how to simplify things at compile time. Well, how was I going to do that? Of course, I knew the rules of how to simplify regular Boolean algebra, but it wasn't obvious to me how to express this to the library in a generic way, so I had to think. Well, I took a step back and I figured a good place to start was with the basics. We're doing Boolean algebra, so true and false are the atoms, and here they are in matcher world. They're called always and never. Always is the matcher that returns true, whatever you give it, and never is the matcher that always returns false. And you can see these are both matchers. They're function objects that take messages and return booleans. It's just that we don't mind what kind of message it is. Okay, so that was easy. So we have an expression template. If we know, for example, that some matcher inside there is always going to turn out true, we could transform the tree and replace it with an always. And that might mean that we can simplify further. Here's an example. Here you can see the tree representing A and not B or C. Now A, B, and C could themselves be arbitrary matchers, including and OR terms. Now, if we know that C is true, then we know that not B or C is true, because you've got a true in an OR term. So the whole OR term becomes true. And if we know that, then we know that the AND matcher at the top would collapse to just A, because it would be A and true. I should say at this point that this matcher library is designed to work with another library that computes indices on the fields and uses that ahead of the matching to partially dispatch. So it is possible by the time we get to evaluating a matcher that we will know it will be true because it involves a field we already indexed on. And we'll know this at compile time. Well, the next thing is to write a simplify function, and then we can overload it for the and, or, and not matchers. The default simplify function does nothing at all to simplify, it just returns the matcher it's given if we don't know any better. What does simplify look like for AND? Well, we know what to do if either side is always or never. First, we'll recursively simplify each side of the AND. Then if either side is never, we know that the AND itself will be never. If either side is always, the result of the AND will be the other side. Otherwise, well, we simplified both sides and we can't do any better than that, so we AND them together. And we can write a very similar looking function for OR. And we can go to Wikipedia and find all the rules of Boolean algebra and code them up. There are quite a lot. Here are some of them. There are even more, considering that we have to deal with each expression being both ways round. For example, A and true simplifies to A, and true and A also simplifies to A. This gets verbose pretty quickly, and it's quite limited in what it can simplify. How do we simplify less than 5 or greater or equal 5? We know this should simplify to always, but these matches are different types. How does the library simplify this? If we could know that these matches are complements of each other, we could simplify the expression. Maybe we can do that by customizing the application of not. So I introduced a customization point, negate. Instead of just wrapping a not around a matcher, I call a negate function which can be customized, and here's our new operator overload for not on a matcher. Now instead of just returning a not t, we're calling this negate function, which we can overload. Well, the default thing to do is still to wrap a not around the negated matcher. That's what we were doing before, that's easy enough. But now there's another overload that springs to mind. Negating a not matcher can just return the original matcher inside, instead of double wrapping it with not, so that's nice. Now I think I can write an overload for a relational matcher. What I need to do is return a new matcher whose operation is the inverse relational operation. And I can code up a simple function with a half a dozen if const extra branches inside it to deal with inverting each of the half dozen relational function objects. Now the library has a generic idea of negation, which means it understands those relationships between the relational matchers, and it can simplify things like this expression by normal Boolean algebra methods. Have you noticed that so far all the functions we've written have been just a few lines, or at most 1 or 2 lines in each of a few if const extra branches? This is a good sign that we're going down the right compositional path. Okay, this next problem on my list of problems that I was thinking about was a bit harder. So again, we know as humans that less than 5 and less than 7 is really the same thing as just less than 5, because if a field is less than 5, it's necessarily also less than 7. And there should be no need to evaluate the second matcher here. So I thought about this and I had an idea that took me about a week to incubate. And here's where we have a quiz. A quiz in a recorded talk. Yeah, the questions are easy, I hope. Ah, you say, but are the answers easy? Yes. Okay, first question. If I have a thing of type A, and I have a function from A's to B's, can I make a B? By the way, some folks aren't familiar with this syntax for a function pointer type. This is just a function pointer type using trailing return syntax. So given this, can I make a B? And the answer is yes, of course. It's not a trick question. I can just call the function with the A. Next question, and it's really the same question, slightly different. If I have an A and a function from A's to B's, this time, can I make a pair of A and B? And the answer is yes again. A is copyable. I'm not bothered about non-copyable types here. Those are C++isms. We can call the function with the A to get the B, and then we have a pair of A and B. And now the last question in this short quiz. This time I have a variant of A and B, and the same function from A's to B's. Can I make a B now? and the answer is still yes. If the variant already contains a b, I'm done. But if it contains an a, I use the function again to make the b. Okay, hopefully that was quite an easy quiz, but what was the point of it? Well, believe it or not, you just did Boolean algebra, even if it didn't seem like it. Here's the function from a to b. Now, what does that function arrow mean? It means implies. It's the same thing as Boolean implication. Let's reinterpret the quiz. When we say, I have an a, we're saying a is true. And when we say, I have a function from a to b, we're saying a implies b is true. And when we say, can I make a b, we're asking, is b true? When we say, can I make a pair of a and b, we're saying, is a and b true? And when we say, I have a variant of a and b, we're saying a or b is true. In each of these cases, the type interpretation maps directly to a Boolean algebra interpretation, and we call this the Curry-Howard correspondence. This is what reasoning with types means, and the good news is that you already knew the answers to those questions. You just might not have recognized that they were Boolean algebra questions. So you already have an intuition for implication. Let's take a closer look at it. The idea I had was that I could use implication to simplify. So what is implication? It's just another binary Boolean operation. We're all pretty familiar with and or. Implies is just a different truth table. And here they all are. The third column is a and b, the fourth column is a or b, and the last column is a implies b. Now, thinking about implication can be confusing for some reason. I think because we tend to say things like, if A then B, which obscures the idea that A implies B is a proposition. It might be true or false. So it's sometimes easier to think just of implication as a plain old Boolean operator. There are a couple of implication propositions we can take note of, though. Here is the first one, the easy one. Anything implies true is a true proposition. And we can see this from the non-grayed outlines of the truth table. False implies true is true, and true implies true is true. The second proposition is harder to intuit, but it's clear from the truth table. False implies anything is a true proposition. False implies false is true, and false implies true is also true. False implies anything is hard to grok, so here are a few explanations that might help. I can say all unicorns have pink polka dots. This is a true statement. Unicorns don't exist. The set of extant unicorns is the empty set, so any statement I make about unicorns is true. Please disregard the fact that unicorns you see in movies are white. Here's another example of implication. It's raining implies the ground is wet. What would make this statement false? Only if it's raining and the ground is not wet. If it's not raining, the ground might still be wet, or it might not be, and the statement is still true either way. Another way to think about this is in terms of sets. It's raining implies the ground is wet is another way to say the set of times when it's raining is a subset of the set of times when the ground is wet. Okay, so how does this tie into simplification? Well, I wrote out the truth tables for and, or, and implies next to each other. And here's what I realized. If A implies B is true, then A and B is the same as A, as you see here in columns 1 and 3. And A or B is the same as B, as you can see in columns 2 and 4. So I realized I could use implication to simplify expressions. So let's look at how that can work. Here's one of my original problems. Why does this simplify to just less than 5? Because if x is less than 5, it is less than 7. In other words, less than 5 implies less than 7 is a true proposition. And if we can express that to the library, it will be able to simplify. Okay, I thought let's make a customization point for implies. The default is that a matter implies itself. It doesn't imply a matcher of a different type. And once more, this is just a one-liner. This code is saying that X implies X is a true proposition. Well, we also have true and false. We call them always and never. So we can code up the facts about implication that we saw just now. And here's the C++. This is saying any matcher implies always is true. And in the second case, never implies any matcher is also true. Now, if you're really paying attention, you might notice that these two overloads produce an ambiguity if we try to compute never implies always, because in that case, both of these overloads will match with equal precedence. But we can solve that problem easily enough with an overload that deals specifically with that case. So just one for never implies always. We can also warrant implication involving OR terms. This is saying a matcher M implies A or B if and only if M implies A or M implies B. And we can warrant implication involving AND terms. A and B implies M if and only if A implies M or B implies M. Both of these functions are fairly easy to prove with a half dozen lines each of Boolean algebra, but that slide didn't make the cut for this version of the talk. We can also implement implication between our relational matches. This is the form of our less than 5 and less than 7 problem. Less than 5 implies less than 7 is the same proposition as 5 less than 7. Strictly, it's 5 less than or equal to 7, but we already took care of the case that a matcher implies itself. So this is the implementation of implies for relational matches. It uses the relational operator on the values, another one-liner. In fact, we can go further than implication between matches with the same relational operators, because we know about relationships between less than and less than or equal to, for example. So we can add a few functions for the short list of those kinds of combinations. This is what simplified looked like for an AND term earlier. Now it looks like this. We've genericized it in terms of the implies and negate customization points. If either side implies the other, the AND term collapses to the appropriate side. If either side implies the negation of the other, the AND term must be false, or never. Otherwise, the sides have no relationship that we know about, and it just remains as an AND term. And you can imagine a similar overload for OR terms. It turns out that this does the trick. Using implication in this way gives us a huge helping of Boolean algebra simplifications. We wrote maybe a dozen functions, some containing a few if-const-expr cases. I think no case was more than a one-liner. And what we got was a generic ability to simplify any matcher expression, and the ability to define matchers outside the library, provide a couple of overloads for them, and treat them the same. And all of this simplification happens at compile time. At this point, I had a couple of observations. One was that I might once have thought of A implies B as merely not A or B. They have the same truth tables. But I was really using implication as a building block here. I think it wouldn't really have been possible to do the same manipulations if I didn't use implication this way. I'm not evaluating the terms, I'm warranting the truth of the implication proposition. A few days after getting to this point, I realized something else. We're manipulating matchers. Matchers are predicates. So implies is a higher order function. And because the matcher semantics are encoded in their types, we're able to actually evaluate implies without evaluating the matchers, which is a rarity in my experience. Most higher order functions eventually evaluate the functions they're given. So after doing this, I continued with my life. And then, a few weeks later, I had another realization. I realized that implication defines a partial ordering on matchers. Can functions in general be ordered? No, but matchers are predicates. A given matcher matches some things and not others. Matcher A might match fewer things than matcher B, and that can give us a partial order based on how many things are matched. If everything that B matches is also matched by A, then B implies A. And under an ordering interpretation, this also means that B is less than or equal to A. And this gives us another way to interpret that tricky false implies anything. False is never the matcher that matches nothing, or the empty set. And of course, the empty set is a subset of any set, so it's less than everything. And this is another way to say that false implies anything. And this is what the C++ looks like for ordering matchers. This is the spaceship operator. If neither matcher implies the other, they're unordered. We can't do anything with them. But otherwise, they can be ordered according to which way around the implications are. This is where my talk must end. There is a lot more here, but that's another talk. Actually, more than one other talk. As I said earlier, this library, the matchers library, fits in with another library that computes indices on fields at compile time, so that runtime dispatch can be very cheap and easy. But we don't want to tie together the knowledge of which fields are indexed with the matcher code. The goal here is to be able to express matchers easily, and then use field indices to speed up selected use cases. And the details of how we do that are in the longer version of this talk and in Luke Valenti's companion talk. And we do a lot more with Boolean algebra to make the indexing library and the matching library mesh together nicely at compile time without having to overly constrain our expressions because of performance concerns. It only remains for me to thank you all and leave you with my conclusions. Like many of us, I learned Boolean algebra as a teenager, and I didn't really give it much thought after that. I thought it was too trivial to bother with much when I was trying to apply myself to complex problems. But it really does underlie everything we do, and implication is a very important operation that is typically given even less mindshare. But every time we write a function, we are expressing an implication. And when we really understand and apply Boolean algebra, it can do some surprising and powerful things. Thank you very much for listening.
All right, thanks very much for that talk, Ben. That was really fascinating. If you have a link to the GitHub, can you drop it in the chat? And if you have any more questions for Ben, feel free to direct them to him. Before I move on to my talk, we do have a survey. If you can fill that in, that would really help us. Let us know what we can do differently next year. And with that, I'm going to move on straight to my talk. I embedded a programming language in debug information, and I'm going to tell you all about it. Okay, so if you have any questions while I'm talking, please drop them in chat. I will keep one eye on it for the whole time. I cover some pretty weird stuff, so if you want anything clarified, just let me know and I'll get to it. An alternative title for this talk is Dwarf Shenanigans. The agenda for today: I'm going to give you an intro to the Dwarf debug information format, which is where I embedded an interpreter. I'm going to tell you how I embedded custom programs more generally in Dwarf. I'm going to give you an intro to the BF programming language, which is the language I embedded, and then how I implemented a BF interpreter inside Dwarf. First off, why? Why did I do this? Why am I telling you? Well, I was writing a Dwarf parser, and I was thinking, hey, this thing looks suspiciously Turing complete. I wonder if I can write a programming language in it. And it turns out you can if you throw enough time and gray hairs at it. But I wanted to learn about executable and debug information formats, or learn more about them. And this is kind of what I hope you'll get out of the talk, a bit of knowledge about how this stuff works under the covers. Also, it was just a challenge to implement a language in such a constrained environment, and I had to come up with and use a lot of neat tricks in order to do so. But mostly it was fun, and I hope you have fun learning about it. Okay, an intro to Dwarf. Not like this. So Dwarf information is a binary encoded format for linking machine code back to the source code that produced it. And it does this in a number of different ways. It has a line table, which links the source lines to machine instructions. Like if you want to set a breakpoint on line 9 of cat.cpp, then you need to know to which machine instruction that corresponds in the running program. Similarly, if you want to set a breakpoint on the pet cat function, then you need to know where the code for that lives. Most importantly for us is locating variables at runtime, because the way that variable locations are encoded in dwarf is with dwarf expressions, not like this. So dwarf expressions tell us where a variable lives. They can also restore registers in stack unwinding information, but primarily interested in this form for now. And this can be in a number of different places, right? It could be in a register, could be at some address in memory, but it could also be a bit more cluster and then dereferencing the address that's there and then adding some offset to the result, for example. And it could be even more complicated. It could be stored, different parts of the data can be stored in different locations. So dwarf expressions can be quite complex, and they support expressing these complex locations. So dwarf expressions are a binary encoded sequence of instructions that run on a stack. Dash Candy says, are there dwarves in Microsoft formats, or is this just in ELF? Yeah, I'm talking about Linux systems today, and I will be getting to ELF later. So let's look at an example of a dwarf expression. Say we want to do exactly what I just said, read the R12 register, dereference the address there, and then add some offset to the result. I can issue the DWOP breg12 with 0 as an offset. And on the right-hand side is kind of what the stack might look like. Here's a value which might be in that register. Then I can dereference that by issuing the DWOP deref instruction, and that will read that address and push the value which is there back to the top of the stack. Now I want to add an offset, so I can push that offset onto the stack. So now we have 2 values on the stack. And then I can use DWOP add to pop the top 2 values, add them together, and push the result. So you can see kind of how we build up a program with these operations, and they're fairly generic. And you might be able to see how we can start thinking about how we can use this stack to implement our programming language. But that's getting ahead of ourselves. Importantly, we also have control flow, quite limited control flow, but control flow nonetheless. We can branch, which is a conditional branch, and skip, which is an unconditional branch. And these basically move the program counter forward or backward by a given offset. Reasonably straightforward. Okay, so how did I embed the interpreter? Now, there's a problem. Dwarf expressions are encoded in binary, and I don't want to handwrite that. That would be a nightmare. And this was already a nightmare enough as it was. So I wrote an assembler which takes textual representation of a dwarf expression and converts it into a binary representation of that same dwarf expression. And it's mostly fairly simple. The kind of core of the assembler is just a massive if-else statement, which handles all the opcodes. So if the opcode is DWOP adder, I get rid of the prefix just so I don't have to write that everywhere. Then I just output the DWOP adder opcode into some byte stream. I then parse the address operand as a 64-bit integer and output that into the byte stream. Fairly straightforward. There could also be simpler ones like DWOP deref, which you saw on the previous slide, and that doesn't take any operands, so I just output the opcode. Or some will take operands which have to be encoded with a different sized integer, for example, like deref size. Just like DWOP adder, it takes an integral argument, but in this case, it has to be encoded as an unsigned 8-bit integer. So I have to make sure I pass the right size. And this kind of follows for the rest of the opcodes. There's only a few dozen, so it's not too bad. Slightly more interesting is I want to support things like this, having labels and comments so that I can kind of make my own functions and say, hey, this is kind of what the input to this function should be. This is what the stack should look like when this function is called. And then, down at the bottom there, I've got a skip instruction. And instead of giving that an offset, I want to give it a label and have the assembler work out what the byte offsets are. Because if I write that myself, every time I change my code, I'm just going to have to modify these, and it's going to be a nightmare. Okay, so how do I do that? I basically loop over all of the instructions in the dwarf expression. If it starts with a dot and ends with a colon, then that's a label. So I just make a note of the label's name and where its position is in the byte stream. If the line is not empty and it doesn't start with a hash because I use those for comments, then I encode the instruction, and that uses just that massive if-else statement that you saw earlier. Something to draw your attention to is this final argument, fix-ups. This is how I handle references to labels, because you might jump to a label which is only defined further down the program, so it hasn't been read yet. We don't know where it's going to live in the byte stream. So I just keep track of all of those. And then right at the end, after I've dealt with all of the instructions, I loop through all of these fix-ups. I get the byte offset into my byte vector at which the label exists. I work out the difference between where the label is and where the reference is, encode that as a 16-bit integer because that's what the standard expects, and just copy that over. I write some zeros into the byte stream in the first place and then copy the real data over here. So that kind of works. We can now generate binary dwarf expressions, but where we put them? The answer is ELF files. So let's talk about ELF, not like this. So ELF files are how binaries are encoded on Linux. They have a header, which describes high-level information, such as, oh, I am an ELF file, and I am an executable, and I am for 64-bit systems, all that kind of stuff. And it has sections, which describe areas relevant to linking together multiple object files and libraries, and then segments, which describe areas relevant to program loading, such as, hey, operating system, please put this code and this data in this position in virtual memory when you load my program. We have a question on endianness. I am just dealing with 64-bit Linux, sorry, x64 on Linux. So I just say everything is little endian, and I don't care about other platforms because it's difficult enough doing it for a single platform. There's also how small can you make an ELF file? I can't remember exactly, but they can be very, very small. Like you don't even need section headers. You can strip those out. It can be pretty minimal. But we will see a bit of this later. So that's how it goes. These are the most important sections that I need for my needs. I have the .debug lock section, which is where dwarf expressions live, or well, where some dwarf expressions can live, but it's the easiest place to put really big dwarf expressions, and I need really big dwarf expressions. Then there's the .debug info section, which is where the majority of dwarf information usually lives. And in there, I put entry for a dwarbf program variable, and that is how I link together my interpreter program and the program which I'm interpreting. That program I store in .strtab, which is just the string table. So this is going to get loaded into my into the address space when the regular x64 program is loaded by the operating system. Okay, so I'm going to show you a bunch of code of kind of what I did when I built my ELF file. I decided to do it completely by hand because taking an existing ELF file and modifying it is a massive pain because there's a lot of cross-references between everything. And as soon as you like insert bytes into there, then you mess up everything. It's not fun. So I just wrote an entire ELF file by hand. So So I'm going to show you a bunch of the code. I don't expect you to read through all of it and understand everything I'm doing. This is just to give you a kind of feel for the nonsense and shenanigans that I got to. So first off, I had to define an ELF header. Up the top there is the magic number, which says, hey, I'm an ELF file. There's the file type, which is executable. I say that it's for x86-64, and then a bunch of other metadata about the ELF file. One other thing to note here is that OXFFFF that I put for the section table file offset. The section header table lives at the bottom of the ELF file. So I don't know where it's going to be yet because I don't know exactly how much data I'm going to be writing into this ELF file. So I just leave it as OXFFF and I fill it in later. I have to make section headers for all of the sections. I only have maybe like 8 or 9 sections. So here's one for the .debug lock section. It has type program bits. I don't know what the file size is going to be yet, so I leave that as OXFFFF. I have to have some x64 code so that can get loaded, and so that my if I run this through GDB, that GDB can stop on some valid instructions. So this is essentially a return 0 in x64 assembly, x64 machine code, which I just encode as a byte array. And then I need my program headers, which describe segments. So I have a single program header, which tells the loader to load both that x64 code you just saw and the string table, which holds the BF program that I'm going to be interpreting. Then I also have to write the dwarf information by hand, which is kind of a nightmare, and it's huge. So I'm only showing you a tiny bit. This bit is where I am describing the layout of the dwarbf program variable entry. I'm saying it has a name and it has a location, and that location, that's where I'm going to stick my interpreter. Then once I've done all of that, defined all my data, I have to write it out to a file. So I basically keep track of a big byte stream. I insert the ELF header into the byte stream. I insert the program headers because those come next. I insert the text section. After I've inserted the text section, I know where it's going to live. So I update the text section header, which I will write into the byte stream later on, and go on doing that with all of the data I need for my ELF file. And after all that's done, I finally write this out to just a regular file on the file system. I just open a file in binary mode, blit it out, and we're done. With all of that, I can run I call DW assemble, which will assemble some dwarf expression into a binary that contains the dwarf expression. And if I run the file program on it, which is just a regular Linux thing, which tells you about the file, then it says, hey, this is a 64-bit ELF file for x86-64. So Linux is reasonably happy that we've written a valid ELF file or something that looks valid-ish. We can even use tools like readelf and dwarfdump for understanding more about the file. So I'll show you a few bits and pieces. This is readelf minus capital S, which gives you the section headers. You can note that you can see the most important ones. Here, the .stir tab, which holds the BF program, the .debug lock, which holds my interpreter, and the .debug info, which links them together. What happens if you run it through strip? I think it would stop working because I rely on some stuff that strip would strip out. But I haven't tried it. This is dwarf dump, which gives you a dump of the dwarf information. So you can see this is the .debug info section, and it contains a dwarbf program variable, and the location of that points at the .debug lock section, and the top instruction there is the address of the BF program in the string table, or at least where it will be in virtual memory when this thing is loaded. And then that ... is the rest of my interpreter, which I'll show you in a bit. And then the final thing is I can look at the string table, and you'll note this mess of symbols. This is my BF program. Might not look like a program, but this is a program, and now I'm going to tell you all about this language. So, intro to BF. This is what you just saw laid out on a single line. I'm not going to walk through it. This is a program to calculate the 6th Fibonacci number, which is 8. And this is the entire program. We'll tell you about the language. It runs on a theoretically infinite tape of cells. Every cell is a single byte, goes from 0 to 255. And there's a pointer, which points at one cell at a given time. So there's 8 instructions in BF. There is left, which moves the pointer to the left. There is right, which moves the pointer to the right. There's plus, which increments the value currently being pointed at. There is minus, which decrements the value currently pointed at. Then there's IO instructions. There's comma for reading one character from standard in, closed in square brackets, and anything between these square brackets will be repeatedly executed until the value which is pointed at by the pointer is 0. And that's pretty much the entire language. All right, writing the interpreter. Cameron says, I still believe that BF is the best language for anyone to start with if you're looking to write your first interpreter/compiler. I agree. I have a talk which I gave at CPPP where I wrote an entire x64 BF compiler from scratch on stage. And it's such a fun language. Yes, we're doing a BF interpreter. BF is best friend language. Yes, thank you, Josh. All right, writing the interpreter. So I'm not going to show you much of the code for the interpreter, because it's really gnarly and horrible. I'm going to show you some of the algorithms that I used in implementing it. Now, the top left here is that infinite BF tape. The bottom left is the BF program with a null terminator at the end, just to show when it's finished. And the right-hand side is the contents of the dwarf expression stack. All right. So I want to interpret the first instruction of my BF program, which is right, which should move the pointer to the right. I hold on the stack 2 values right now. The top value is the index of the cell I'm currently pointing at, which is 0. And the bottom value is the current BF instruction character that I'm pointing at. So if I want to move the BF pointer to the right, I just increment the top value on the stack by 1. And then I have to move to the next instruction. So I flip the 2 elements on the top of the stack, add 1 to here, and flip it back. And now I'm ready for the next instruction, which is the left instruction, which I just decrement the value on top of the stack. And then flip again, increment the character pointer, and we're pointing at null, so we're done. We just interpreted a BF program. Now, left and right are several orders of magnitude simpler than the rest of the instructions. So that's why I walked through them first. But after I did this, I came across several difficulties. I mean, I am like implementing a programming language in a language designed for simple address computation, so it was never going to be a walk in the park. But some of the main problems are there's no way to do I/O, which is bad. There's no function calls, kind of. There are some function call expression instructions in dwarf expressions, but they're not very well supported. One of them is not even implementable as it's specified, so I don't use those. There's no way to modify any stack elements beyond the first 3. Now that's a big problem because we have an infinite tape, which we need to be able to modify. So that's not great. I can copy any of the first 256 elements to the top of the stack, which is good, but only with a compile time constant index. All right. I did manage to overcome most of these. I did like quit this project like 3 different times thinking it was not possible, but most of them I overcame. The having no way to do IO, that one you just can't get around. I can't read from standard in and write to standard out. There's just no way to do it. So I don't implement those instructions. Someone finds a way to do it, let me know. Only being able to modify the top 3 elements. This one took me a long time. So I can't just have an infinite tape or like treat each value on the stack as the value of a cell, because I can only modify 3. So what I did was something like this. So again, top left is the BF infinite tape, bottom left is the BF program, right-hand side is the dwarf expression stack. I've already interpreted the first 2 instructions, so we're pointing at this BF cell at index 2. Now you'll notice here I've introduced a new value onto the stack at the bottom there. It's just a bunch of Fs and then a byte of zeros. So what I do is I maintain a list of tagged memory update records. And that list is terminated by this special bunch of Fs, 2 zeros. This is like an end of list marker or sentinel, whatever. So if I want to interpret the plus instruction, which should add 1 to the currently pointed at cell, what I do is I read my memory record update list. The first value there currently, there's only 1 value. It's the end of list marker. So I know that I do not have a current memory record for the cell at index 2. So I create one. There's some bitwise operations that I can do with dwarf expressions. So I use those to create kind of a tagged value. So most of the integer is dedicated to the cell index, which is 2. And then the final byte, because these cells only use a single byte, that stores the value of the cell. So the top of the stack currently says the value of cell at index 2 is 1. And then I rotate that into place because I can, remember, manipulate the top 3 elements of the stack. And this is how I represent my BF memory. So then I interpret the write instruction, which moves the pointer over. And now I have another plus instruction to interpret. I do the same thing. I start reading the list. Here we do have a valid record, but it doesn't match the cell we're currently pointing at. 2 is not equal to 3. So we look at the next one, which is, again, the end of list marker. So we create a new update record and rotate it into place. So now you can kind of see how this builds up. We move the pointer left to do the left instruction. And now things go a little bit differently. For our final plus instruction, we, again, start reading list. We got a record for cell 3, which doesn't match. This time, we got a record which matches the cell we're currently pointing at. So we do a bunch of bitwise operations to update the record and rotate it into place. Note, I cannot modify the old record. I have to push a new one because I can't modify anything past the top 3 values. So I create a new record for every single variable modification. So I can only support like 250 odd variable modifications, which is not a lot, but hey, it's what I'm working with. So I was pretty pleased with that. It works pretty well. Having compile time indices only for indexing the stack. That's kind of bad because I need to be able to walk down that memory update list to find the relevant entries. So this is done with the dwop pick instruction, which takes some compile time index, which is a single byte. But I want to do this at runtime. So I wrote basically a massive switch statement in a dwarf expression. I called this pick table, and this takes one argument, which means that it has the runtime index you push to the top of the stack before you jump to pick table. And I just do a bunch of checks. I check, I only start at number 3 because that's the first stack value that I want to be able to copy up to the top. So I check the argument against 3. If it is 3, I call pick 3. Otherwise, I check against 4. And if it's 4, I call pick 4. And so on, so on, so on, so on, up to 255. It's horrible. I wrote a Python script to generate this code for me, but it works. So yeah, you can translate runtime indices to compile time indices. Another problem, no function calls. For this, I basically emulate return addresses. The problem here is that I need that pick table implementation like 6 different places in the code, and I don't want to have 6 different versions of the pick table because that starts to become intractable. You can only jump. You only have 2 bytes for jump offsets, and that starts to become a problem when you have these pick tables, which are too large. So I basically implement return addresses. So in the implementation of plus, when that needs to call the pick table, it first pushes 0 to the top of the stack, and then right after it calls the pick table, it has this pick table plus ret label. The implementation of minus pushes 1 instead, and then has a pick table minus ret afterwards. And I do similar things for the other 4 places I need the pick table, pushing 0, 1, 2, 3, 4, or 5. So that gives a kind of identifier for where to jump back to after the pick table is finished. So at the end of the implementation of pick table, I just do a switch statement again, basically. Check against 0. If it is 0, I jump back to plus ret. Otherwise, I check against 1. If it was 1, I jump back to minus ret, all the way to the rest of them. So apart from the I/O, that's our problem solved, more or less. And with that, I can get my BF program, which generates the 6th Fibonacci number. I can run dwar BF on it to embed interpreter and this program into an executable. I can run GDB. This is plain GDB. I did not modify it in any way. I can run plain GDB on this program. I can run start I, which just starts and immediately halts the program. And I can say, hey, what's the address of the dwar BF program variable? And because my interpreter is stored in the location information for that variable, then when GDB sees this, it's like, oh, hey, yeah, I'll run this dwarf expression, which happens to be a programming language interpreter, and gives me back the result 8, which is the correct answer. So this gave it's about 2,800 instructions of dwarf expression. It gave me several gray hairs. Like I said, I gave up several times before I got this to work. It does need about 80,000 instructions to be executed to calculate the 6th Fibonacci number. So it's not the most efficient programming language, but it kind of works. It's pretty cool. So thanks very much for listening. And if you do want to check out the code, then you can find it here at github.com/tartanllama/dwarbf. And yeah, if you have any questions, feel free to drop them in chat. I will be around. Yeah, that was a fun project to work on. So with my talk done, we're going to move on to the next session, which is on enhancing C++ development with Copilot Chat with Sina McKinjay. And yeah, we will move over straight away.
Hi everyone, welcome to my talk. Today we're going to be showcasing enhancing C++ development with Copilot. Before we get started, I wanted to give a quick introduction. My name is Sina McKinjay and I'm a product manager for C++ Copilot in Visual Studio and VS Code. Copilot is a tool that can assist you at various points in your C++ development journey. Today we're going to introduce what these tools are, showcase them in a live demo using it in C++ code in Visual Studio, and then wrap up with tips and tricks we suggest for improving results and how some of these workflows translate to VS Code as well. So before we get started, you may be asking, what exactly is Copilot? And how is Copilot similar to or different from Copilot Chat? And how are both of these tools different from IntelliSense? Let's walk through it. So there are many different tools available to assist you with your development with the C++ language in Visual Studio and VS Code. At the first level is IntelliSense. What IntelliSense does is suggest hints for your code based on what you are typing and provides quick parameter information on hover over symbols and in drop-down lists. So, for example here, I'm writing a function that computes the square root of a number. IntelliSense pops up and has suggestions for variable types and variable names such as double and num1. This can be really helpful when you are working with files and want to know the different variable types or function names that you can access, as well as completions for structure. What GitHub Copilot does is it takes this a step further. Copilot provides AI-powered code completions that generate entire code snippets. Just start typing and Copilot can adapt to generate the desired code. It goes beyond IntelliSense by providing context-aware suggestions and allows for natural language prompts via comments in your code to generate these code snippets. For example, with the same square root function, as I start typing out double S, it is able to perceive that I am writing a square root function and generates the appropriate variable names and error scenarios. Copilot Chat takes the power of Copilot and augments it via a chat interface and features integrated into Visual Studio and VS Code that allow you to interact with your code via natural language. It is designed for programming tasks and can automatically access related content in your code within your IDE, unlike other more generic chatbots. So, here you can see that I have that same square root function and I'm able to pull up a chat interface and ask Copilot to generate a square root function, and it loads the results in that familiar diff viewer so that I can view and edit the generated code by Copilot Chat before accepting. In addition to the chat interface, there are various features that are integrated into Visual Studio that we'll cover today that are powered by Copilot Chat to meet the developer where they are in their coding process so that they can minimize time, context, switching, and remain focused on the task at hand. To get access to this tooling, you'll need to have an active GitHub Copilot subscription. GitHub Copilot and Copilot Chat are now automatically included with Visual Studio as a recommended component under a singular GitHub Copilot extension, as long as you have at a minimum version 17.10 Preview 3 of Visual Studio installed. In VS Code, these are currently separate extensions that you need to download via the extension marketplace. To learn more about accessing Copilot Chat in Visual Studio, please visit aka.ms/copilotchatVS. And to learn more about accessing Copilot Chat in VS Code, please visit aka.ms/copilotchatVSCode. Copilot Chat has the potential to provide AI-powered assistance at multiple areas in your coding journey with C++. It has many commands and features that hook well into these use cases, but you can accomplish them through many different types of workflows, so whatever works best for your mental model. It can assist with the early areas of interacting with new and unfamiliar code. For example, it can explain any unfamiliar snippets of code to you when prompted and help you locate the relevant functions you're looking for. It can also assist with generating new code and tests. If you're encountering errors with your build or code, passing in the error code to Copilot Chat can nudge you in the right direction of what you may need to do to fix it. Additionally, you can pass in file contexts or highlighted code snippets and ask Copilot Chat to refactor this existing code. Copilot Chat also has the functionality to generate AI-powered commit messages, so you don't need to spend time recounting and typing up every change you made in a particular commit to Git. Now let's take a look at how Copilot Chat can help us with some of these common tasks in a demo in Visual Studio. Okay, so let's hop into the demo. Because this is a live demo and Copilot suggestions are probabilistic, not deterministic, this demo will focus on showcasing both Copilot functionality and tips for iterating when you don't necessarily get the response you want. Additionally, we recommend reviewing results generated by AI, as I will in this demo. So let's go over to Visual Studio. Okay, So here I have the Jork repository open, and what Jork is it's an application that allows the user to input different types of commands, and it outputs the results of these different commands. So what I want to do today is I want to add some functionality to this Jork application with the help of Copilot. So upon first glance, I'm noticing that there are some build errors with my Jork repository. Copilot Chat can help you with resolving these errors. So I can navigate to this Copilot Chat pane on the right-hand side, and this is what I can use to help with fixing these errors. Before we get started with that, just some things to showcase with Copilot Chat is that there are these / commands available for you, and a lot of these can help with those use cases that we discussed earlier. So for example, there's explain for explaining code, generate for generating code, and test for generating tests. Additionally, as you're prompt crafting, you'll add references to the prompt via the pound command. So you can add specific documents that you're working with to ensure that Copilot Chat can scope to this context and provide dynamic responses. But let's first focus on fixing the error that I'm seeing in my error list. To do so, I can type /fix, and then I can copy over the error code and paste this into Copilot Chat. Then Copilot Chat can nudge me in the right direction of what I need to do to resolve this error. So it's telling me I'll need to reading through this, add assets.ixx for the Jork repository or Jork executable in your CMake list.txt. So I'm looking through my Jork executable, and I do notice that my assets.ixx file is missing from here. So I will add that to my CMake lists.txt file and reconfigure Jork with this. Something to note is that a .ixx file is actually a module file in C++. So this works similar to a header file, and it is a module object for different dependencies that you can then import into your C++ code. So in this case, it's trying to import jork.assets, but it was not able to detect that .ixx file, so it was breaking the build. So it looks like the configuring is done, and I can build the Jork executable now. Something else to note in the Copilot Chat pane is that you can always look at the references that Copilot Chat sent to the model via the references icon on the bottom. So for example, here I'm seeing that it sent my CMake list.txt file as a reference to provide this response to me. Also, to the right of it is a helpful feedback mechanism to the model itself. So since the build succeeded, I can say that this was helpful for me, and I can give a thumbs up to the model, and that way I can also train the model on what is helpful for me, what is not helpful for me, and provide that feedback to the model itself. Now that the build succeeded, I can run the application, and we can take a look at the different types of things that we want to edit with the application itself and use Copilot for at a higher level. So that's just going to take a second to open up. Okay, so now the Jork executable has loaded, and I'm seeing at a first glance that this main menu that is for the application does have some color to it, but I don't think it is as optimized as it could be for those who are visually impaired. So one scope of edits I would like to make to this application is to improve this title screen so that those who are visually impaired can read it better. I'll press return to begin, and I can type out help to see the available commands to me. So it seems that that pet command seems particularly interesting to me right now. I'll try petting maybe a cat, and I can see that I pet Marshmallow on his little head and he looks pleased. I'll try petting a dog now, and I can't pet a dog. So something else that I want to do using Copilot Chat is add some more functionality to that pet case in the code. So I'll stop this application for now and close out of this. Close out of that window and navigate over to my main.h file, which is where my game logic is handled. So something else that Copilot Chat can assist me with is navigating my code. So I want to make some edits to my pet case, so I can ask Copilot, where is the pet case handled in pound main.h? And Copilot can help me understand where exactly my code is handling the pet case. So it's saying that there's this doPet method in the game class that checks for if the object is marshmallow or cat. And then if it is not, it says that it outputs a localized string that the player can't pet the cat. So that looks like exactly where I want to make my edits to. So I will navigate just down to do pet and make these changes via Copilot Chat. There's multiple ways where you can generate code, and it really just depends on what you're trying to do and what your mental model looks like. So in this first example, I can highlight all the code and right click and invoke Copilot via right click Ask Copilot or Alt/, and I can say generate the dog case, and then Copilot Chat will dynamically look at that snippet and add a dog case to the code. So that'll load in a little diff viewer, and I can look and it says I can pet the dog, and it also updates the existing comment to say if the object is not a pet or dog, cat or dog, you cannot pet the dog. So I can also invoke Copilot via comments. So what I can do is I can enter and I can add functionality via comments, and Copilot can then automatically generate the code snippets. So I can say if the object is an elephant, you can pet the elephant. And then delete this, and then if I start typing, Copilot will show up with the dynamic elephant suggestions, and then I can save these changes. Okay, so now that I have these new strings generated for pet dog and pet elephant, I need to add these to my localization files for localization. So I need to add them to the strings.cpp file and strings.ixx file. So I can right click and ask Copilot to generate the localization instances of the dog and elephant case in pound strings.cpp. And that will call upon Copilot Chat to add these new files for me. So it added a dog and elephant strings for me. This is where Copilot can be really helpful with generating this boilerplate code, because this looks good, but I want to add a little bit more color to the strings outputted. So it set up the structure for me, but I can then say, the dog licks your hand manually, and then the elephant trumpets loudly. And so that way I can save these changes and then have Copilot assist me with that. Then I'll just go over to strings.ixx, and I will quickly just type up the pet dog file, and then the inline string key, pet elephant, and then I'll save these two files, and then now my strings are localized with these new functionality. Now that I have these two new cases handled, I actually want to also add unit tests for them. So what I can do is I can right click the same code and ask Copilot via the /test command now to generate unit tests for the dog and elephant case. And I already had some unit tests written in this application, and Copilot will actually dynamically even change, as you can see, like my do my pet dog Case used to say I could not pet it, but now it says I can. And I'm able to also pet the elephant. So I will add these here and I will save these changes, and I can change over to my Jork test executable and build this executable and run it and see if these new unit tests will run with my code. Okay. So while that's building, something that's really exciting and really helpful whenever you're navigating these larger repos is when you get buried in code that is referencing each other and calling upon each other, you can sometimes want to remember what exactly different symbols mean or different methods are. And this is where we have a really exciting new preview feature with Copilot Chat called On-the-Fly Docs that can help you with that. And what On-the-Fly Docs is basically you can hover over any method. So for example, this do pet method we've been working with, and ask Copilot to tell me more about what this is. So here it says, the doPet function in the game namespace takes a string representing an object as an argument and returns a message based on whether the object is a cat, dog, or elephant, including the result of the attempting to pet the object. So this can be really helpful whenever I'm navigating repos and I want to check on what different symbols might mean, what they mean in a bigger picture. And so this can be really helpful. So we really recommend trying out this new preview feature with C++ code and letting us know how it can help you with your navigation. So the build succeeded, and I can then run the Jork tests and see if these unit tests that I now generated for the dog and elephant are able to pass with the help of Copilot. So that way the generated code by Copilot and the generated tests are all looking good for my new functionality. So I'm seeing that it's loading and all tests pass, 4 assertions in 1 test case. So looks great and everything looks great there. Now that that's done, we've handled adding the new functionality to the petting object. We're going to now switch gears and update the title screen to be better for those visually impaired. So I can navigate down to the loop component, and this is where the game loop logic is handled. Here, another way that Copilot can help you understand what your code does is you can highlight a specific function and you can ask Copilot to explain what this does. And that can explain here that it is the loop function and it continuously processes user input and updates the game state until the game is exited. And SDL eventID is handling SDL events, and property is declared to represent the color of the text, and it checks if the main menu texture has been loaded, and uses that specific property color for the text of you may only go down. So this looks like where I want to edit to update the specific colors with my main menu. So I'll exit out of that and go into that. Something to just call out, what SDL event and SDL color are is they're a part of a package called SDL, and SDL helps you handle different like keyboard inputs, handles color rendering, and it is a package that this application depends on via VC package and has a VC package.json file to include. So this is what really handles that like game logic of me typing in commands and so on. So now I am looking at these first 2 events, and it's SDL eventID and SDL color property. I always like to leave code better than I found it, and upon first glance, these do not seem like very descriptive variable names, so I would like to rename those. Something that's really exciting is that we have C++ support for AI rename suggestions, so that I don't need to spend the time thinking of what possibly could be a descriptive and appropriate variable name for these variables, but instead I can invoke Copilot via the rename dialog to generate these variable names for me. So I can go here and I can right click and press rename, and I can invoke Copilot via the sparkle icon to request rename AI generated rename suggestions. So something that seems good is game event, and I can preview and apply those changes. And then for this property, I can right click and rename, and I'll invoke rename suggestions here. And they said that this was the text color, so I think text color would be a great name for that, and I can apply those changes as well. So I was able to rename my C++ variables following normal coding conventions and also making them more descriptive at the same time. So this has been really helpful to have C++ support for AI rename suggestions. Now I want to change the color of the text and the renderer to be better for those visually impaired. I can select the code, so the relevant code here, and ask Copilot, can you edit the text color and the render color to be better for those visually impaired? And this can help me because a task like this could take a lot of time because I would have to navigate to the internet, figure out, for example, like what would be good colors for those visually impaired, and then figure out what the hex code for that particular color would be. So here Copilot was super helpful. It was able to tell me it changed the text color to white and it changed the renderer color to black. So I can save those changes and rerun my application and see how the updates I made are actually being processed. So I'll run the application and take a look at all of that. So in summary, what we've done is we have updated the text colors to be better for those visually impaired, and we added pet functionality to the game. So the application is loading. All right. Upon first glance, the main menu looks a lot better. That contrast seems very good and updated to better standards. And then if I return in the application and I say pet cat, I can still pet Marshmallow. If I pet the dog, I can pet the dog. And if I pet something didn't add functionality for like a rabbit, it still outputs that I cannot pet that. So everything looks great. Copilot really helped me with adding functionality to this repository and let me focus on just reviewing the generated code and prompt crafting with Copilot to get the desired results. So now that I have a bunch of changes made to my application, I need to commit these to the Git repository and update the application. So I can navigate over to Git changes. And here I have my branch of all my changes. And so here I want to add a new branch. So I'll name it my changes and create it. And I'll bring over the changes. And I have my branch and I can add all my source file changes here. Something else that Copilot Chat can assist you with is generating an AI commit message. So I can hover over this sparkle icon with a pencil and have Copilot generate an AI generated commit message for all my changes. That way I can just focus on reviewing the commit message generated, maybe make some tweaks here or there based on what is generated, and I don't really need to recount every specific edit I made. So it says I updated the do pet functionality to include conditions for petting a dog and an elephant. I added clarity in variable names and color changes. Corresponding test cases and main tests were updated for these new conditions. New strings were added to strings.cpp and .ixx for when the player pets a dog and elephant. And then the assets.ixx file was added to the cmakelist.txt file for the jork executable. And I'll just delete the jork test executable because that portion is not accurate. So I'll save that and everything looks good and I can stage my commits and basically was able to and basically was able to generate my code and update the Git repository quicker than ever thanks to Copilot in Visual Studio. So going back over to the presentation, so we saw some tips to improve results, but in general, we recommend opening any relevant files to improve Copilot's performance, as it takes these open files into context. We also recommend iterating with prompts to get closer to your desired results, and you can read more about this at aka.ms/gh prompt crafting. You can use the pound command to scope Copilot chat to specific file context. So as you saw today, I use that to scope it to find files in a specific file and so on. And as I have said, always review results generated by AI. Copilot chat is here to assist you and let you focus on reviewing generated code, but it is AI, so it's not always perfect. If you're interested in learning about real-life C++ workflows that have been used by teams, please check out the links above, aka.ms/ttd copilot and aka.ms/ttd copilot chat, because these have been really successful workflows used in real-life code by teams. We also recommend using / commands when you're using some of the common use cases highlighted today. These are tailored and designed to help perform common tasks like /explain to get code explanations, /generate to generate new code, /fix to propose fixes for a particular problem, and then /test to create unit tests. Today we showcased Copilot in Visual Studio, but it is similarly integrated into VS Code if you use that as your IDE for C++ development. For example, it has many similarities like using / commands for performing actions and the same usage of pound variables to add specific file context. You can invoke Copilot chat inline and through the chat window. VS Code also has support for AI-powered rename suggestions for C++ and Git commit messages. Some notable differences are that VS Code has agents available to provide more dynamic context to Copilot chat. There is a workspace agent that scans your workspace and dynamically finds relevant snippets to pass in as context to Copilot chat. This could be useful when asking overall questions about your code base and locating code. For example, we could have used this earlier when searching for the pet case in our code. There's also a VS Code agent that allows you to ask Copilot questions about the IDE itself, which can be helpful for learning settings and navigating the code editor. VS Code also has Copilot chat integrated into errors, so you can fix and explain using Copilot whenever you see red squiggles, rather than having to pass the error code into chat like you saw earlier today. To learn more about using C++ in VS Code and get started with it, please check out our video at ak.ms/cpp VS Code Copilot video. We covered a lot of ground in 30 minutes, so let's summarize. Copilot and Copilot Chat are AI-powered tools that are tailored to your programming tests. Copilot provides you with auto-generated code completions while you are coding to assist with repetitive or boilerplate coding. Copilot Chat has features and chat interface to interact with AI connected to your IDE experience. Copilot Chat is deeply integrated into your IDE and has the potential to help C++ developers with numerous tasks like navigating code, including that new preview support for on-the-fly docs to preview short summaries of C++ symbols, generating code and tests, refactoring existing code, including the new support for AI-powered rename suggestions for C++, and generating commit messages. Some ways we recommend improving results is by iterating with your prompts when necessary, using / commands, and then opening any relevant files whenever interacting with Copilot. So I'd like to thank you all for attending my talk. Our team is working really hard to improve C++ integrations with Copilot in Visual Studio and VS Code, so please let us know any feedback on your experience or things you'd like to see. Our team is available on X at VisualC, and my handle is Sinem __Akunja. You can also always reach out to us via email at visualcpp@microsoft.com. Thank you all.
Great. Thanks very much for that talk, Sinam. Feel free to drop any more questions you have in chat, and we will make sure that they get answered. Our final talk for the day, and I'm delighted we're 2 minutes behind schedule only. We're like pretty much exactly on time. So our final talk for today is Zachary Henkel, who's going to give us an update on adopting header units in Microsoft Word. Take it away, Zach.
Thanks very much, Cy. Happy to be with all of you here today. Thank you if you're attending live or if you're watching this after the fact. I'm Zachary Henkel. I'm an engineer on Microsoft's core architecture team. So now you know why Cy selected me to be here today. They wanted one more cat to get on screen. I'll be giving this progress report on adopting header units in Word. It's a topic that I've talked about a couple times before. There's a blog, series of blogs that I've done with Cameron to Camera on the compiler team, and also who is joining us in chat today. If you have questions, Cameron can try to get them answered while I'm presenting. Hopefully we can get those links up on screen if you want to. Oh, there they are, perfect. If you'd like to dive deeper in them, it's not required that you've read them, just if you want some background later on. I'm not going to keep you in suspense waiting for the performance numbers that we've been promising for a long time. After adopting header units in Word, the worst case that we found is approximately a 1% regression in compilation speed. The best case is 21% improvement. And I'll spend the rest of the time talking about the scenarios that produce these results. Before we get into that, though, I want to give a little bit of background. So what's the problem that we're trying to solve by adopting header units? Of course, the answer is we want to reduce the amount of time developers spend sword fighting. I'm sure everyone's seen this before. As C++ developers, we're always on the lookout for tools and techniques that will improve build speed. In Office today, the biggest gains from developers only building a portion of the full repository. We call that partial builds internally. So Word developer is only required to build the code that makes up Word and some of its closely related libraries. The other big improvement is employing a precompiled header. And as I just noticed Cameron said, precompiled headers are a 30-year-old technology. So keep that in mind as we're talking about header units, which have only been on the scene for 5 years. There is still a lot of opportunities we're uncovering to continue improving and optimizing. So what are header units? The short version is that header units are a binary representation of a header file. At least with the MSVC compiler, it will produce the same format as named modules, IFC format. But unlike named modules, it includes both, will include macro information that can be both a pro and a con. The important thing for Office, though, is that they can be adopted with minimal source file changes because we compile for all of the Office platforms out of a single monorepo. I guess I'm getting ahead of myself. That's the next slide. But we needed to be able to do this without having to have a lot of invasive changes. So there's a translate include flag for the MSVC compiler. And then there's an IFC map, which can help you build up a large number of these translate includes. Both of those are available on the Learn Microsoft site on the compiler documentation. So this is kind of under the covers. What that translate include winds up doing is turning the pound include into an import directive. So the short version of what Microsoft is, give you a little bit of background here. If you want to see a lot more detail, I have a presentation that I gave at CPPCon 2022. That's up on YouTube. Again, I'll go through just the kind of the key points right here. It's about 100 million lines of native code. We compile for 3 major platforms, Windows, Apple, and Android. And because of that, we have 2 compilers, MSVC for Windows and Clang for Apple and Android. And of course, those are not exactly the same Clang either, because the vendors take snapshots at different times. They do things to cherry pick fixes or add platform specific things. One note, I'm probably going to slip up during this presentation and talk about liblets. Again, there's a ton of that in the CVPCon video that I gave earlier, but you can easily think of them for the purposes of this talk as kind of nicely packaged libraries that are shared code within Office. Oh, all right. So what are the conditions that we set when we started the experiment? So like I mentioned when I was talking about the attractiveness of header units, we couldn't have intrusive source file changes. I'm not saying that no source file changes were required. For the most part, we had found very virtuous changes that needed to be done. Creating a header unit would force the file to be compiled in isolation, and we'd find tons of cases where headers would be missing all the required includes, either because they were provided by a downstream precompiled header, or you're just getting lucky because any consumer's include block would just happen to be in the right order that was taking care of them for you. Any amount of build logic and command line changes were going to be okay. A lot of our build unit logic is distinctly per platform. So when we were authoring header unit support only for Windows at this time, it didn't really impose a large burden on the other platforms. And then it was easy to mask the changes required for staged adoption. It could all just get hidden in the build logic itself. So what was the big hypothesis when we got started? Header units would demonstrably improve inner loop build speed for engineers working on Microsoft Word. So let's pick that apart a little bit. The focus is specifically on inner loop speed. How fast can a developer edit code on their local box, rebuild the relevant portions of Word, and get to validating their change? And a bit of foreshadowing, I'd like to note that inner loop builds are almost always debug builds. Word was our first target because of one of the things that's required for header units, and this is something that was called out in the blog post. You need to have uniform build arguments. It's going to lock in all of the compiler flags and preprocessor definitions as you create a header unit. So you need to make sure that any projects or code that would be consuming them agrees with what was set when you were creating them. Word already had a high level of consistency with a set of those preprocessor definitions and compiler flags, and the low-level libraries that became our first header units. Word wasn't the only candidate application, and hopefully I can talk about some other projects where header units can be adopted in a future presentation or blog post. So this is what Word's physical code layout, at least as it relates to what we'll be talking about with header units. There are two precompiled headers that the code can select between. MinPCH is extremely lightweight. It contains the standard library, Windows.h, of course, some common Word internal helpers, and a very small subset of upstream functionality. Those Office headers that are included in here are limited to very low-level things, some common data structures, platform code, nothing customer-facing. If you count all the transitive includes inside of MinPCH, it's only about 250 files. It's also not particularly widely used inside of Word. Only about 2% of the files choose this as their PCH. Word shared is the complete opposite extreme. It captures nearly every upstream header, with only some minimal holdbacks for test headers that try to do clever things with macros and things like that. It contains about 2,500 files if you're counting all the transitive includes. Makes Word shared a pretty challenging test for header units just because of the breadth of code that's being compiled there. And the other thing in terms of compilation speed is that the Word engineers have spent a lot of time looking with build insights to make sure that the PCH has maximum effectiveness. So how does this diagram change after we adopt header units? We create a header unit for the standard library, and as I mentioned before, some low-level libraries that are already header units. combine them with the existing contents of min.pch or word shared, and then create one single header unit out of each. There are no changes. We just took what was in there and converted it to become a header unit. The existing includes get imported to an import statement for the case of like the standard library and the low-level ones via translate include, and that's it. And then also where you would normally have like pound include min.pch or pound include word shared.h, those will also be translated via translate include into an import statement. So for the experiment design, we have internally we use Build Excel as our build engine and found several of its capabilities well suited to setting up benchmarks. The general flow of a test was as follows. Perform a full build of Word. This is done so that all the dependencies required just to invoke the compiler created successfully on disk. Choose whether it's going to be a PCH or header unit test. Then I would disable build caching, run all the compiler invocations, and do it 7 times. It's easy to do with Build Excel. You can isolate just things that are labeled, and we label all of our compilations. I did 7 times so I could throw out the highest and the lowest measurements in any given set. And then I gathered just the CPU time spent by the compiler. One of the things that we noticed from the start of the experiment, though, is that the measurements were going to be very noisy, because if they take a long time to run, you know, anything could be happening on that box. Our IT could force a scan. The scheduler, which isn't deterministic, would make a particularly good choice to favor header units or precompiled headers. So we needed to do this repeatedly. So I repeated it every night on 3 unique boxes for 3 weeks. I wound up with a data set of 15 different invocations times 3, so 45 across all of these. Here's the equipment that I use for testing, since I mentioned there was 3 different boxes. The most powerful of these, Office, we affectionately call them build the world machines. They're for developers who are working on things that are going to be across all of Office. It's a single CPU, 64 threads, roughly 4 gigahertz peak clock, 256 gigs of RAM. There's a boot SSD in there, an NVMe SSD, and then there are multiple SSD data drives set up with software RAID. Specifically, this is Microsoft storage spaces in simple mode. Simple is like RAID 0, so you have speed, but there's no redundancy. The physical workstation reflects what a developer working on an application team like Word would have for their primary development workstation. 32 threads, again, about a 4 gigahertz peak clock, 128 gigs of RAM, and a similar setup to the BTW, just you have fewer RAID drives. I think these are, for most of them, there are 2 or 3. The BTW has 6 of them. And then the final class of machine I test against is Microsoft DevBox. This is actually a publicly available product that Microsoft sells. It's a virtual machine running in Azure. The VM provides 16 threads, 3.5 gigahertz peak clock speed, 64 gigs of RAM. And in this case, there's only a single drive from both the OS and source. All the Microsoft Dev boxes run on Azure Premium SSDs, the P30 SKU. There are other options, but these are the ones that are available in Office. So here's what the data looks like for building all of Word. Word's roughly 6,000 files. The BTW did well, and you can see there's error bars on some of these where you can see a little bit of the noise, or it kind of reflects the noise that's inside of here. The physical workstation was just about even. This is like, I think, negative 0.1%. The MDB machine shows the measurable regression, kind of just about 1%. So if you notice, or if you call back to the second slide, this is what I mentioned for the worst performance. This is it right here on the MDB machine compiling all of Word. But this isn't the best result that I talked about. That's because recompiling every file in Word isn't the typical experience for a developer. Typically, you'd be working on an individual feature. You'd be making a bug fix, small change. You just need to recompile a handful of files and then be ready to go. To do a better job simulating those workflows, I asked for some of the most active investment areas in Word and found 2 good candidates to measure. So the first of these I'm just going to call folder A. It consists of around 300 files. With this, you can see the BTW pulls way ahead. This is about 11%. The typical developer box and the VM gain both show a nice gain, above or below 3%. And then the other area that I was told about, I'm going to just call folder B. This is 200 files. And then this is where we get that largest improvement that I talked about. This is over 20% on the BTW. And then the physical workstation starts to really pull ahead about 9%. And then the VM, a small but noticeable improvement at 1.3%. What does this all mean? So one thing you could say, and I'm sure all the developers in Office would be happy if this was the takeaway, is that all developers should have server class hardware. Unfortunately, that's not particularly realistic, so we have to dig a little bit deeper. So what's going on? There must be some kind of common factor among these 3 machines that explains why we see the difference in performance. Was it the CPU? Well, I don't think so. Both the physical machine and the BTW had very similar CPUs, but different performance. Peak clock was off by 100 megahertz, but there was the same vendor, same architecture, same CPU generation. So I'm not going to say it's the CPU. What about the RAM? Well, we tried the physical development machine with some results that I didn't show because ultimately they didn't actually show any measurable difference versus what you actually were getting with kind of the standard amount of RAM in that machine. What about the storage? Well, this is where I think it is for 2 reasons. First is that we did some internal tests because I just kind of asked for some off-the-shelf hardware to start doing my benchmarks with. And one of the things that we noticed was a difference between hardware RAID and software RAID, which is why I had called it out in the earlier slide talking about what the machines were that we used. The hardware vendor sort of has, if you look around on the internet, is known for not having good hardware performance. And so switching from using their low quality hardware RAID to the software RAID, we got a 40% speed up once you were switching from one to the other. Plus, I was running, some artificial benchmarking software that just does kind of storage benchmarkings, and it was significantly higher results using with that benchmarking software. 2.5 times better for read perf, 3.2% better on write perf. So clearly improving the storage system helped with this as well. But why is storage speed what is dominating? So I gave you a clue earlier. So after some investigation, we noticed that debugging information was causing additional writes under header units that weren't there under the PCH. Oh, sorry. So how much extra information are we talking about? We looked at the size of the object files on disk, and they were a lot bigger. So the sum of all of the object files created for Word was 22% larger consuming header units versus consuming a PCH. The median increase was 25%, and then the largest was almost 9,000% larger under header units. That's not a typo. So I have to thank Kavern and Gabby, who I see quite active in chat over on my other screen here, for helping me investigate this from the compiler side. The biggest offender we found was a pair of enormous enums being written into the object files. And when I say enormous, one of them was 10,000 entries, the other was 30,000 entries. So don't do that, friends. One of them was an enum containing all of the command IDs for every single app in Office. The other one was data points for doing performance, correlating performance data. So yeah, it was entirely too much. The long-term plan will be to teach the toolchain how to reference this information directly from the IFC instead of having to duplicate it into each object file. The short-term plan was the very high-tech solution of simply excluding the two headers that included this information from the PCH. Here's what it looks like after we did so. The total object file increase goes down to 18%, median down to 22%, and then the largest is only like 1,700% bigger. Still not where we want it to be, but it did help quite a bit. It does emphasize that there's more work to be done by the compiler, and it can't only be solved by editing Office headers. I'd also then like to call out that all of the data that I showed in the charts above, that was after editing the files to remove these enormous enums. One of the other things that I'd like to talk out or call out here is that this also explains the differences between folder A and folder B. Folder B actually wrote 14% more data than folder A, which is why you see a larger performance increase across all the boxes, or I guess not all of the boxes, but I guess the more resource constrained boxes in that with that test set. So that's enough of the unfortunate news. How about some good news? Beyond build speed, header units have additional advantages. First is that they're portable. So precompiled headers produced by MSVC must be created locally in order for them to successfully be consumed. Header units don't have this limitation. It would be possible to employ that partial technique that I talked about earlier that we used in Office. You could have a project upstream of Word that created the two precompiled headers. And then any developer would simply be able to have the contents brought down from the build lab, from our cloud infrastructure, and then skip having to create them at all. The second is that IFC is amenable to tooling. We have a specification for this. We provide an SDK for it. Cameron had a pre-conference video for this if you'd like to see more about it. And then finally, oh, and thanks for sharing that link. The header units and modules are considerably smaller than a PCH. How much smaller? 90 to 95%. I've been gathering data on this for quite a while, and every time I see these numbers, I still wind up being shocked. You might point out that it's not fair to do an apples to apples comparison between the final header units, like the ones that are in Word, and a PCH, because the Word header units have references to upstream header units. They compose very nicely. You don't have to duplicate information. It just knows how to go look it up in a required dependent IFC. So that's fine. I agree with you. Let's bring up the numbers if you add up everything upstream as well. I think this is still pretty good at 77 and 88%. So what do we have to do to take this further and keep realizing these gains? So unfortunately, there's an incremental linker bug that we uncovered. The fix is pending. It'll be in the very next release of the 17.8 branch in May. Unfortunately, if incremental linking fails, it falls back to do a full link, and that one's just destroying your kind of inner loop build speed. So we had to pause the experiment for now. If you're going to be adopting 17.10, it's available right away from the RTM version here. Then the other is the big call out here, which is to reuse the debugging information from the IFC. This is more invasive than some of the other things that some of the other requests that we've had to the compiler team for fixes and improvements, because it requires the entire tool chain to work together on this. The linker will have to be updated. The PDB writer will have to be updated for this. And so unfortunately, because of that, this is work that's underway, but we don't have any date to share today about when it'll be available. We'll be sure to talk very loudly about this when it's ready to go. And then on the Office side, what do we have to do? As I mentioned earlier, we have additional opportunities to test header unit consumption in some of these end applications beyond Word. We'd like to start this in the very near future. At the same time, we want to continue making low-level libraries into header units. Before doing so, we have to remove our equivalent of like a root inc folder. It's a collection of headers that don't share a single logical responsibility. Once these headers can find a new home, their component libraries can have a header unit created for them. And then if that's unlocked, we can create the shared precomp that powers so much of our shared code as a header unit. And that inflection point will open the floodgates to making more header units. As I called out in the blog post and have talked about earlier, the biggest thing you have to do in order to be able to see these gains is not ask the compiler to do extra work deduplicating information for you. And that's why you have to take this kind of bottom-up approach to make sure that you don't textually include things into multiple header units, because that's just going to waste the compiler's time, and thus your time. And then finally, we have to continue striving for consistent build flags. We've done a lot of the work to do kind of internal marking to make sure that we understand where we have disagreements, and it's just a matter of then doing the actual work to make sure that all of those things are consistent, and then additional projects can be incorporate header units. And of course, I'll close with the same motto that we've had since we first started talking about this. We want to build all the header units. And I hope to continue sharing the details of this journey with you until all of the header units are built in Office. Thank you.
Great, thanks so much. It's really cool to see all of the numbers on that, and see that even adopting header units and not full name modules gets you a fairly substantial speed up to your inner loop. That's really exciting.
Yep, thanks so much, Simon.
Yeah, all right. See you later, Zach. Okay, and that brings us to a close of the day. Thank you, everyone that has joined. If you have any more questions, feel free to drop them in chat. I believe we can maybe still answer them. I cannot remember. Or find us on Twitter or email. We do have a survey, which would be really great if you can fill it in to let us know what we can do differently next year. You should see the QR code on your screens now. And on the run-up to the conference, we published a whole bunch of pre-recorded videos. So please go and check those out as well. There's like 15 or 16 videos. The link is on the screen right now. And they're on a whole host of C++ topics. The videos for the sessions you saw today will all be up on YouTube, so you can watch them again or reference them. And thanks very much, everyone, for joining us, and see you next year.